today to us.
Yeah.
So thank you very much, Steven, for coming.
Yes, thank you, Daniele. Hi, everybody. My name is Steven, and thank you again to Daniele. It's my honor to be here to give a presentation to everybody, and from not just in Bell Lab, but many parts of the university here. I'm very honored. So today, I'm a research fellow at the Alan Turing Institute, and I'm also a research fellow at the University College of London, Bartlett. And today I'll talk about discovering urban features and estimating real estate values from urban street images. And it's the kind of research I've been doing in the last 1.5 years at the Turing. So this is my outline of the presentation. So it is evident that the design of the built environment influences many aspects of our lives: where to live and play, which route to navigate, and which city to live in. For example, where would you rather live? The image on the left or the image on the right? What design elements are in the more desirable ones? So these are some of the questions that I wanted to address during my fellowship at the Turing. And it motivates a lot of my research that I'll talk about today. So discussions regarding what urban design elements lead to better cities has largely been theoretical and largely been supported quantitatively only by small-scale studies. So in the two studies here, interviews have been asked about which style of architecture is more desirable, or which area do people like to live in. So these early kind of researchers focus on very, very small-scale interviews and surveys. So as we know, that is not adequate because it's a much larger sample that the rise of machine learning methods, which had achieved human-level accuracy in tasks including machine vision and natural language processing, coupled with large-scale data availability, can potentially fill these gaps. So I have two examples here. On the one on the left is a recent research from DeepMind, where they use Street View images to navigate in the city, where it uses reinforcement learning agents. And the one on the right, which is probably a research that people here also know about, Street Score, from some researchers in MIT, Naik. And of course, the research from Daniele on happy cities, all related to this using of machine learning methods in urban geography. However, currently, research in discovering design knowledge have been quite sparse. So this is kind of where my angle comes in, is to have, can we discover urban design knowledge from using these methods and data sets? As a result, my research aims to use machine learning methods to discover urban design characteristics and to make linkages with outcomes such as economic progress and residential well-being. So this is my aim of my research. And I have divided my talk into basically two papers. On the former is about urban design characteristics, and on the latter is about economic outcome, which is a lot more about my recent research on predicting house price in London. So for the first part, I'll talk about urban design characteristics. And I published a paper in 2017 in Six Spatial, and I'm also publishing a paper coming up in IJGIS about this topic. So this is supposed to be moving, but it's not. Active frontage is an important element in urban design, and it's defined as ground floor buildings that have windows and doors as opposed to blank walls, fences, and garages. The greater the number of doors and windows a street has, the livelier and safer the street feels. So imagine walking on the street on the left, and imagine walking on the street on the right. Which one do you feel safer? Which one do you want to, which property do you want to buy? Which street do you want to live in? I think it's quite obvious, probably the one on the right, the one on the left, not the one on the right. So despite being advocated in planning guidance, previous research on the topic had been limited. Firstly, in terms of scale, and secondly, in terms of establishing what benefits these design elements provide. To collect the data necessary to evaluate street frontage quality at the city level is costly and time-consuming. As a result, we cast this as a machine vision problem. So in this kind of first paper, what I did is I classified a front-facing street image into these four classes. The one on the left is blank frontages. The second one is one side active. On the third one is both side active, and the fourth one is non-urban. So it's a very simple classification problem of these four classes. There are two aims in this research. The first is to study the extent urban design characteristics such as frontage quality can be retrieved from both street imagery and synthetic street image data. The second is to interpret these models, test how well it generalizes across geographies, and testing the extent it relates with socioeconomic indicators such as house price or well-being. So this is the architecture of the first model that I'm going to talk about. This London SFN model I called here is a deep CNN, which was trained using Google Street View images and synthetic images in classifying a front-facing street view into 4 classes. The 4 classes on the right: blank, single active, both active, and non-urban. And I've tested 4 different architectures of this setup, including VGG16, ResNet 50, Inception V3, and Exception. So basically on the inputs are Google Street View image data and synthetic image data that I created from City Engine. And I put that into a set of convolutional and fully connected layers, and it outputs a probability of whether it is blank, single active, both active, or non-urban. And then I chose, using a softmax classifier, the maximum probability one to be the one selected for the image. So this is a very basic CNN architecture, which takes images as its inputs, and I ran it with these in parameters, which uses very typical stochastic gradient descent and using the cross-entropy loss function since it's a multi-class classification problem.
Steven, where do you take the synthetic ones?
I developed a parametric city model,
Okay.
and then I output, so I can easily put walls and no walls to determine if it's active or blank.
But starting from the Google Street, or?
No. I created there was templates in City Engine where it creates cities for you, and then from that I just put in walls and no walls. So it wasn't synthetically created from like
your
a
label for the street view, basically.
Yes.
You're saying that's a type of thing, and then.
Yeah.
Okay, I see.
So it's not like a GAN where you generate the image from. This is basically a 3D model, and then you put walls and no walls to signify if it's active or blank. So part of my research aim here is to test, can we replace street images with synthetic data? Because this takes a long time to classify and label, and this is very quickly. You can generate this really quickly because in City Engine is a parametric software that generates loads of images of however type you want to you create.
Input of what? So an input of what? So are you starting from OpenStreetMap? So let's say that I have a street segment down the corner. So how do you generate the synthetic City Engine image?
So City Engine is a software owned by Esri now. Mm-hmm. So basically, it was started from research at ETH, and they basically you can give it a street and it generates buildings for you from the parameters that you set in the beginning.
But do they have a knowledge about what the street is about?
No, it just generates a city for you. And then I can put a parameter to say that does it have active or blank frontage, for example.
Okay.
So you can create a grid, and you can say, I want randomly this type of buildings, and it scatters it randomly across the landscape in the city, in a virtual city. And in the virtual city, you can give parameters about active or non-active. You can have other parameters. Say if you create a very complex model, you can say, I want to have more windows, I want to have more doors, or you can have architectural styles, say for example stone or wood and so forth.
So let's say you generate millions of images, to them you associate the 4 labels, and you go in the CNN and you say, can I predict for an unseen synthetic image, what type is it out of the 4?
Yes.
Okay.
Yes. So the first model I ran was just a Google Street View image. Yeah. The second model I ran was just a synthetic image, and the third model I ran was the 2 together. And the results are that when you just run the synthetic image, the results are not very good. So basically, the synthetic images, if you just use that to train your model, it cannot predict a street view if it's active or not.
An unseen street view. Yeah.
No. However, if you combine the 2, it actually achieves the best results. So on the bottom right, you achieve about a 93% accuracy if a front-facing street view image is an active, non-active, or single-site active or non-urban. It's a bit of an improvement if we just use Street View images. So what this result tells us is that you cannot really just rely on, like, unless your synthetic model is really, really powerful, you cannot just rely on that. However, you can augment it on the real images, and it makes training a lot better. So you don't need to spend as much time in, I don't know, labeling your data. You can use the synthetic data as part of your data set to do the classification. So it minimizes the time a lot in training.
What is the mixture fraction in your?
So in this model, it was about like 20%. It was maximum. Like more than that, it actually didn't.
20% of
yeah.
synthetic data. Or
yeah, 20% synthetic data and 80% real data. Like the more synthetic, after that, I think the more synthetic doesn't really help. It actually made it worse. But perhaps there's perhaps more work can be done into creating these synthetic data, because there should be a lot more parameters that you can tune to make it as close to London as possible. But part of my research is want to create a general framework that would act in any city. So I'll show a bit of the result on the generalization afterwards. Yeah. Yes.
Just the last thing, are all the label data synthetic in your case?
No. The Google Street View image are manually labeled, and the synthetic one is automatically labeled. Yeah. And then I've also, I wanted to know, like there's 7% errors in the data. So, and then I wanted to know where is the CNN actually looking. So this is basically what I call a matrix. It's like a matrix on where the image is accurate and not accurate. So on the diagonals, they are the areas where they basically, it should be red if it's accurate. For example, when it's blank, it sees the walls. When it's active, it sees the facades. And when it's single side active, it sees one side of the facade. So on the diagonals, this visualization basically shows where in the image does it get activated from the CNN model. So you can see the off diagonals is when they have errors in the model. So it seems like single side active and both active has some confusion of where it gets activated. So this is where the 7% error came from. Like this is some techniques that people often uses to visualize what went wrong in the CNN model. And this kind of was quite intriguing for me, because these CNN models is a very black box model. So it's very important, I think, which I'll explain later. To actually better understand these CNN models is very important as a future research direction. And so after using the 93% model, I have calculated for the rest of London. So this is kind of the map that you get for the rest of London of where it's active, like Regent Street or Kensington High Street, or inactive, like Kingsland Road or Harbour Quays. And they relate to how we imagine the city. Places like the West End is very active, while places like Canary Wharf is very inactive. So from the visualization, it also allows us to better understand the model. So not just visualize the CNN layers, you can also just visualize your model from a geographic perspective, and you can review some information on how accurate your model is. And then I then generalize this across different cities around the world, and I use the model of London, and then I test it on around the different cities. And this is why I wanted to create a generic parametric model. The reason was so that I can use a model that can predict any city in the world. However, what I realized is that cities like, I don't know, Kyoto, Tokyo, and Hong Kong achieve the worst accuracy. So this makes sense because culturally they're very different. What is active or inactive in different cultures are also very different. So I'm currently in the process of how much training data I need from different geographical regions can allow me to create a much more generalizable framework. And also, yeah, so these are the results so in Europe, the results are a bit better, like in Paris, but the results are a lot worse when you go to places like Tokyo and Hong Kong. So I'm also looking at localization and detection at the moment. So this is not published yet, but I'm also looking at retrieving different elements of a streetscape, like not just urban or active or trees, but also doors and windows. So to get a more holistic view, because at the moment, a lot of the classification, research that has been done, like ImageNet, has been on very specific things like cats or dogs, or in like the places database in MIT is very general of is an old building or new build. So it hasn't been really gone down to the level of architectural elements. So part of my kind of research agenda is to build up a database that would allow one to also extract design elements from street images. So, so this is kind of my recent work on this topic. So, and I've also related kind of this kind of frontage quality to different elements. For example, scenicness, which is a colleague that has now not at the Turing, but she was at the Turing previously, who looked at scenicness data. So basically, it has a game that asks people if it's scenic or not scenic, and I related the kind of quality of frontage quality to kind of scenicness data. And I found that they obviously correlate. Places that are more active tend to be more scenic, and places that are less active tend to be less scenic. So from kind of this kind of socio-economic relations that has brought me to the second case study, which is about economic outcome. So this is kind of the key research I'm currently working on with a couple of colleagues from the Turing, which is, can we use these street images to actually predict house price? And how much prediction accuracy can you gain from it? So house price in the kind of real estate and urban economic literature is a function of its intangible components such as size, accessibility, amenities, but also on its intangible components such as safety, visual desirability. In the past, studies examining intangibles such as visual character have been sparse. With the even recent advancement in machine learning methods, urban visual features can potentially be retrieved and its effects estimated. So there are two aims to this research topic. The first is to study the extent visual imagery can improve existing hedonic price model using an end-to-end neural network model. So the first aim, can I put in can I just put in images on the input side, and can I get a better prediction in the output side using a complete black box model? So and then on the second aim is to step back a little. Can we actually create a more gray box model where we try to improve the trade-off between interpretability and accuracy, and building a gray box model that uses some parts is like a neural network model and some parts more like an econometric model. So the second latter one is like a hybrid between like a machine learning model in the first part and an econometric model in the second part. So this is the architecture of the black box model. So you have your traditional housing attributes that you control for in any hedonic price model, and that includes size, the number of bedrooms, the age of the building, the accessibility of your dwelling, your school quality, your park proximity, and these are your X's. And on the two additional stream of data here, you have the street view image, which I used already in the previous research, and on satellite image, which I captured from Bing, which is a similar kind of image data, a different kind of image data set. So you get both a ground view and an aerial view. And I plug that into a black box model. So imagine this part to be a black box model, and these are your inputs of your input feature factor. And you have a multi-layer perceptron in your housing features. You have convolutional layers in your street image, and another convolutional layer in your aerial image. And then you concatenate these layers, and then you run again multi-layer perceptron on the end to try to predict your house price. And to try to predict your house price, which is here, which is a function of your attributes, your street image, and your area image. And the loss function is to minimize the mean squared error between your observed house price and your predicted house price.
Sorry.
Yeah.
So the house price
Yeah.
is like
Why?
E1. It's the house price at actual time.
Yeah.
Okay.
Yeah. So there's a year variable as well.
You
Yeah.
have different time periods.
Yeah,
to-
yeah. Yeah, so there's a year variable in, I should have put it here. It should be part of the housing attribute. It's like a more trend variable. So yeah, that's in the loss function as well. That the X includes time. Yeah.
Is that the land registry data here?
Yes.
Land registry
Yeah.
data.
So I've worked with 3 different data sets. One is the nationwide data, which I work with someone in LSE with. But recently, I've been mostly using land registry data because it's much larger. And I combined it with the EPC data, which had a lot of attributes. So I'm using these 3 data sets. Yeah. And then here's the gray box model, what we call the gray box model. So the difference between the previous model and this model is that instead of putting in nonlinearity across your whole architecture, we stopped it here. We stopped it here. So from here onwards, it's more like a traditional econometric model, where you try to predict house price from your housing feature vectors, your visual embedding of the street view, and your aerial embedding of your images. So here, I'm just learning a visual embedding from the house price model to get this function. So the loss function now it includes more like an econometric form, a standard linear form, more like an econometric standard linear form that you'll probably more recognize in an econometric setting, where instead of learning end to end, you learn only up to the visual embeddings, and then from here you run an OLS model at the end. So what's interesting here are these 2 visual embeddings, which is these 2. And then you can then estimate betas for these embeddings. So what's interesting here is that you lose some of the probability accuracy from the black box model of doing end to end, but instead you can build these models to stop at certain points, so that you can get these. It's a bit like it's like these embeddings of an autoencoder. So you have these embeddings now that you can use for different kinds of model. It could be house price model, but it could be also you could correlate it with other aspects of the urban environments. So our kind of aim here is to compare the more black box model here, end to end, to kind of like this semi-gray box model, which combines more like a traditional machine learning model of using CNN to retrieve the visual embeddings, to at the end of using in a more econometric setting. And then you can do traditional statistical inferences on these models better. Yeah.
So there's no which part of the multi-layer processing as you change with these econometric, you take out the back propagation, or still doing back propagation? No.
Yes, it does. It does. It still does. Yeah.
Sorry, the street, what you have on the street and the satellite image. I guess I understand that the satellite adds also the garden or something like that. It's not visible from the street, but there's also significant overlap. So if afterwards you just use it like in a standard OLS regression, don't you run into like multi-collinearity problems? Because you're basically measuring, part of the image is measuring the same thing.
Yeah, very good question from a much more of an econometric point of view. So yes, I think my recent research has been looking at more like looking at collinearity across these elements, and it's something I need to consider a lot more. The 2 do correlate, but not a lot. They don't exactly correlate. So, but I agree. It's probably maybe I need to have another way of retrieving some orthogonal of just these 2, getting of these factors to maybe merge it into a single visual embedding to get rid of these potential multicollinear effects between the street image and the satellite image. Yeah, thank you. And here are the results of your linear kind of house price model, your gray box model, and your black box model. And this is first using a random test set. So this is when I take out 20% of the data and I do a prediction on this test set. And this is a kind of a holdout test of Southwark. So I remove Southwark altogether in the training samples, and I predict on Southwark completely from scratch. So you can see from here that the results of the gray box model is exactly and expectedly between the kind of traditional OLS model and the kind of totally black box nonlinear model. I have done some more recent research at the moment where I'm putting nonlinearity also, but kind of a more interpretable nonlinearity on the housing attributes as well, which achieves like an 80% here in the middle, which does like a nonlinear with these two, but more in a more interpretable way, rather than not knowing what those attributes actually means. And then in Southwark, as you can expect, the results are a lot worse than the random test sets. But again, you see a similar pattern that exists where the totally linear model achieves the worst when compared to the gray box model and the black box model. So what's the nice things when you retrieve these visual embeddings is you can start to visualize and to start to try to understand what these visual embedding means. And then, so for example, this is just a map of the visual embeddings. So these are basically those two together for the entire London. Then you can start to map out, this is kind of like a revealed visual preference map of London from the house price. And you can see that potentially maybe the higher visual preference one has more trees, and maybe the lesser visual preference one has more road. So from this, I then start to analyze how these visual embeddings actually relate to the image itself. So what I've done, I ran a segmentation model of using the street images, which basically gives you where's the sky, building, tree, road, pavement, and pedestrians. And then I relate back to the visual embeddings to get a better understanding on what actually those visual embeddings are. And then you can see, yeah, there's some relationship between the visual embeddings and the number of trees. So it seems like the visual embeddings is capturing something about trees. Not very strongly.
And how many visual embeddings do you have out of the two main components?
So each street has one visual embedding. Now the two visual embedding, one from the street and one from the aerial.
Okay.
Yeah.
So just two values.
Yeah. Two.
With two values, the prediction goes up.
Yeah.
All right.
But that's not the prediction. You're doing the correlation there in the second chart, right? You're finding those. No, next one. Yeah.
Oh, this is just correlate. Yeah, this is just this is just a.
Explaining, right?
Yeah.
But the R-square table, so it's saying that if just two betas extra, you get a jump in R-square.
Yeah. Yeah.
Which is amazing.
Yeah, which is-
because those are two values
Yeah.
only. Then you don't know what they are, and you're trying to explain what
Yeah,
they are.
I'm trying to. Actually, there's a more there's a semi-gray box model here which gets about 80%. So I'm applying more like spline modeling on each features to retrieve the nonlinearity of like a traditional OLS model, and that gets you up to 80%, which is I think quite cool because you don't need to run like an image has 256 pixel by 256 pixel in 3 channels, which is a lot of variables. So you can just reduce that to two values, and you can use that to get up to 80% R-square on a test set, which I think is quite usable. It's quite is quite useful, I think, from especially from an econometric standpoint.
Very economical.
Yeah, economic standpoint.
So the next one, right, so when you have the different colors from green to red,
Yeah.
so that represents one of the...
Yes.
But different degree, so you segment in quartiles or whatever?
Yeah. I use a natural break, and then I just, into those color bands. Yeah, bin it into those color bands. And then relating it to what do those, so I'm currently still at this research stage where I'm trying to explain what do these visual embedding means, because what do these scalar value means. And I haven't, I'm currently working on a web app where I'm trying to ask people to rate these images and then comparing the machine rating and the user rating at the moment. So if anybody's interested to help on the survey, I'll send a link where we're trying to better understand what these machine rating means. Yeah. So to conclude, this research explored 2 applications of deep learning methods on urban data analytics. The first involves classifying urban street frontages using both street view and synthetic image data. The research finds encouraging results using these 2 data sets, with implication in data collection and knowledge discovery. This first research strand argues there's a need to focus on retrieving design knowledge of the built environment as potential implications on policy change and implementation. And what I mean here is that I'm trying to argue there's a need to know not just how safe a street is, as in what street score, but actually what elements of the environment that influences the street score, because there's not enough research into that, because then you can actually use these elements to make policy changes in the environment. The second regresses house price with both housing attributes, street view data, and aerial data. The research finds visual attribute has a significant effect on real estate values. The research also finds the gray box model, which retrieved visual embeddings from the images, were able to achieve positive interpretability accuracy trade-off. These results also shows the potential of this gray box model in giving better latent explanation of the built environment that can be further applied in econometrics and other fields, for example. So that concludes my talk today in my research at the Turing Institute. Thank you. If there's any question, please. Yeah. Yeah.